All right, so you get this information about two different beakers, one that has magnesium nitrate, one that has sodium hydroxide. It gives you concentrations. That's for a different component of the question. But the intermolecular force part is this right here. Basically, it's talking about this diagram, and it tells us that magnesium ionizes in solution to Mg2+, and in this one you'll have Na+ for the sodium. And then it tells you that in beaker 2, sodium has a weaker attraction to water than the magnesium, and you need to explain it using Coulomb's law. So before we go into the actual problem, let's just review what intermolecular forces are to begin with, since I don't think we talked about it since like before break. But the typical type of forces that keep molecules together that we're familiar with are called intramolecular. Okay, so intramolecular, if you remember. And those are like covalent bonds, right? Where the actual elements stick together, they're part of one compound. So they're the same material. Okay? But intermolecular forces, okay, are going to be between separate compounds, separate particles. So you'll have different molecules reacting with each other. They're not actually they're not reacting, but they interact with each other, and they induce movement and attraction, repulsion, because of these things called intermolecular forces. There are three, kind of four, that we talk about. Anyone remember one of them? Yeah, London dispersion forces. Yeah, dipole, right? Dipole. And the last one? Hydrogen bonds, good. Okay. There is another one that that we do talk about, and it's called ion dipole. And it's very similar to dipole. Let's talk about what dipole is real quick. Dipole is where there's an electronegativity difference between the elements in a molecule, and that causes the electrons to kind of congregate towards one side of the molecule. So water is a good example. Oxygen is more electronegative than the hydrogens. So the electrons like to congregate around the oxygen. And since they do that, it creates a partial positive on one side and a partial negative on the other. Okay? Hopefully that is familiar. The way that we also write down or draw it is we draw an arrow with a little perpendicular line right here. So it looks like a plus sign on the partially positive side. And so that's the reason why water will have a attraction to the Mg2+ ion. It's because of the partial negative and the positive. Okay, so before we actually jump into the problem, which intermolecular force out of these four is being demonstrated here? Not H bonds, not dispersion, not dipole, ion dipole. Because look at what we have. We got a dipole right here. Water is a dipole, and what is this? This is an ion. Yeah, so this is ion dipole. Okay, let me give you some examples of the other ones. Let's start with dispersion. Dispersion is electrons move. So sometimes they'll be on one side, sometimes they'll be on the other, and that'll create a partial positive and a partial negative. This is the weakest one, and pretty much every molecule has dispersion to some degree. Okay, dipole is between two polar molecules, so like water. So we talked about how the hydrogen side is partially positive, and the oxygen side is partially negative. Well, if you got another water molecule next to it, right, the partial positive is going to interact with the partial negative, and so on and so forth. That's dipole. Hydrogen bonding is pretty much a really strong dipole. It only occurs when you have a very electronegative element next to hydrogen. It's going to be N, O, and F. Okay, so if you have one of these bonds connected to the rest of the molecule, it's going to create a dipole, very strong partial positive right here, which will interact with other dipoles. Okay, so that's kind of the information. Let's get into the actual problem. So that information is kind of given to you in the problem. It tells you that Mg is attracted to water, and the Na in here is obviously going to be attracted to water. But we're going to explain why Mg is stronger, or it has a stronger intermolecular force than the sodium. And it tells you specifically to refer to Coulomb's law. So in your answer, you have to talk about Coulomb's law to get full credit. Now, some of you guys might not remember Coulomb's law. It was, I think, before Thanksgiving break. So if you guys take out your AP equation sheet and you want to make a note, this right here is Coulomb's law. And nicely, it tells you Coulombic. So Coulomb. God bless you. All right, so let's talk about what Coulomb's law is talking about. Okay, we have this nice little explanation for our variables. So let's talk about what this is. So this right here this force Coulombic has to do with attraction and repulsion. Okay, so basically this part right here tells you if the two things that you're looking at, if they're gonna attract or repel. Okay. All right, it says Q is charge. So that Q is basically just telling you, is it a positive charge? Is it a negative charge? Is it +1, -2, +3, so on and so forth. Okay? And then the R is the separation. So basically it's just the distance, the radius between the two bodies that you are looking at. So in the question, it's basically asking you to compare Mg2+'s attraction with water. And we know this side is partially negative, this side is partially positive, and NA's attraction with water. Okay, and the question is basically asking, why is this Mg2+ and O's intermolecular force stronger than this one here between Na and O? And you have to refer to Coulomb's law. Okay. All right, now it might seem very complicated, but it's actually very simple to use this. Okay, so let's start by plugging in what we have into this formula. So Q1 is the charge of one of the bodies. Let's start with the Mg one. So let's start with this one first. So Q1, let's say that it's the charge of Mg. What's the charge on Mg?
2.
Yeah, +2, right? So very easily, the force is +2 on the top. And then Q2 is not -1 or -2 or anything. We just know it's partially negative, right? So for that, let's just write that it's a negative number. Okay, so this is a minus sign. And then we're just going to write R2 just to talk about how there's some distance between them because they're not completely stuck to each other. All right, for sodium, I'm going to do it in blue just so that we can kind of differentiate more easily. Okay, for sodium, what would Q1 be here if we're talking about the ion? Yeah, +1. The charge is +1 right here, so Q1 would be +1. And then the same thing, the partial negative is right here. Okay, and so we don't have all of the numbers, right? Or all of the variables filled in, but we can kind of compare them with one another because of the charges. So between the two of them, which one do you think is going to have a greater magnitude? Yeah, Mg, right? Because it's +2 versus +1. It's double, right? And so we would write that +2, since it is bigger, Mg is going to have, that's the reason why there's a stronger attraction between the two. Okay, so if we go back to the question is asking the relative charge of the ions. That would be your justification. Your justification would be that when we use Coulomb's law, Mg, since it has a greater charge, it's going to have a greater attraction. And you would just refer to this formula. You guys all done? Just leave right there. Thank you. So part A is talking about the charge of the ions, but part 2 is talking about the relative radii of the ions, the size of the ions. So I'm going to give you guys about 2-3 minutes. See if you guys can try this one on your own, or you can work with the person next to you. I want you to explain using the radii of the ions, Mg and Na, why does Na have a weaker attraction to water than Mg? So see if you can do that. Make sure you refer to Coulomb's law in your answer. So you're going to be using that formula again. So try that out. Okay, so we take a look at number 2. It's talking about the relative radii of the ion. So radius has to do with the size, right? So what we're going to be doing here is we're going to compare the size of the ions. So we're gonna be looking at Mg2+ and Na+. So we're gonna be looking at the size of these two ions, and that's what we're gonna incorporate into the Coulomb's law, which makes sense because Coulomb's law has a variable for size, which is r, radius, right? That's the size of, or half of the diameter. So let's take a look at our periodic table, and we're gonna look at Mg and Na, and we're gonna compare them. All right, so if we take a look at Na and Mg, let's look at the regular ones first before we do the ions. Okay, how many shells do they have? Yeah, so the ions have 2. Normally, they have 3 because they're on the 3rd row, right? But because we're looking at Na+, that valence electron disappears, so it'll have 2. Same thing for Mg, it's on the 3rd row, so it'll have 3, but since it's 2+, you get rid of the 2 valence electrons. So you got 2 electrons. Okay, so you got 2 shells for both of them. Everybody good so far? All right. You got 2 shells, and they're both complete valence shells. So let's do 2 shells for both of them. And they are both going to have 10 electrons because +1 means 11, -1, 10, and then -2 for the Mg. So 10 electrons each. Okay, so the difference between them is going to be the protons, because Na is going to have 11 protons, Mg is going to have 12 protons. Now, we talked about this in one of the units, but what do protons do to the electrons? Yeah, they bring them in, right? They have an attraction, and so they bring it in. So, since they have the same number of electrons, so same amount of electron repulsion, but Mg has 12 protons, is Mg bigger or smaller? Mg is smaller. Okay, even because protons, they have a negligible effect on the size of the atom. What matters is how much nuclear attraction there is. So since it has the same number of shells, same electrons, but more protons, Mg is going to pull the electrons in more. Okay? Make sense? Okay. So if you guys notice, a lot of these problems, they're, it's intermolecular forces, but it's kind of synthesizing a lot of the info that we went over throughout the year. Okay, so let's go back to our little formula. All right, so let's do Mg in red, and we'll do Na in blue. All right, so for Mg, we still know that it's 2+, and it's going to be with a negative number. Okay, and then we're going to do r squared, but before that, let's fill this in right here. And you can use the same one if you'd want. Okay, so for Mg, we know that this number is going to be smaller, and this number right here is going to be bigger. Okay, now, if you notice, it's on the denominator, right? So if a number on the denominator is smaller, what does it do to the overall value of the number? Yeah, it makes it bigger. So since this number is smaller, it's going to actually increase the overall number, and that'll be your justification. You would say something along the lines of Mg is smaller. You talk about in Coulomb's law, radius is in the denominator. Okay, and then smaller denominator is going to equal a larger Coulombic force. Something along those lines. Yeah, what's up? Yeah, pretty much. Yeah. So you'll have to give your answer, and then you would have to justify it. Yeah. But if you take a look at, excuse me, the Google Drive that I gave you with the previous ones, I have the answer keys there, so you'll see kind of what they're looking for. It'll say like 1 point for this, 1 point for that, so on and so forth. All right. So for this one, it is going to be an ion dipole, and the reason why is because we have an ion, right? And water is polar, so it's going to have a dipole. Oops, wrong way. I flipped it. Oh, actually, no, I didn't flip it. Trip. Okay, so there's going to be a partial positive with the water, a partial negative, and so there will be an intermolecular force. So triiodide will have an ion, because this is an ion, dipole. It will have an ion dipole. That is the intermolecular force that it has. Okay, but let's talk about why this has a stronger attraction. If you look at I2, iodide, what intermolecular forces does this one experience? Dispersion. Anything else? No, it is only dispersion. Okay, so dispersion only. And why does it only experience dispersion? It's the same, so what do we call that? Yeah, nonpolar. This is nonpolar. There is no side that has a stronger electronegative charge because they're the same thing. Whereas this one, it has a built-in negative charge, so it's an ion. That's it. That is why. So I2 would actually not dissolve very well in water. Okay, because nonpolar does not dissolve well in polar molecules like water. Same reason why oil doesn't really dissolve in water, because oil is nonpolar. Okay, so we had to draw these Mickeys, so we're going to draw some Mickeys. But first we got to determine what the parts of the Mickeys represent. So we got a white circle and two of these filled-in black circles. And we're talking about water, which is H2O. So what element is the white circle? Oxygen. And what is the filled-in circle? Hydrogen. Okay? So that should be pretty easy. So let's talk about the polarity now. Which side is partially negative?
The O.
The O side is partially negative because O is more electronegative than the hydrogen. All right, so partial negative, partial positive. We know that chloride is negatively charged. So which side is going to face the chloride ion? Yeah, the hydrogen side. So what you should draw is something along these lines. Okay, it doesn't really matter, again, where you put the water molecules. The key thing is that the hydrogen side has to face the chloride side. Okay. Something like that. The answer is because there are two Mr. O's. Actually, it's Mr. O and Mrs. O right here. Yeah, so that's why it is stronger, because we are amazing and nothing can separate us. Now, but for real, it's because both of these sections can form a hydrogen bond. So basically, there is an additional H bonding site. Okay, whereas here, only this section can make an H bond, right? But here, there are two sites that can make a hydrogen bond, and that's the reason why. Okay, so for this one, you're looking at some different elements and their ions, and apparently for a phosphorus ion is larger than neutral phosphorus, and zinc is smaller than a neutral zinc. So basically, it's asking you why one of the ions is larger than the neutral, but why is one of the ions smaller than the neutral? Okay, so in order to do this one, you're going to need to identify what ions are, or at least what type of ion it forms. So if we look at phosphorus, anyone remember what is phosphorus's most common ion?
-3.
Yeah, -3. 3 minus. Okay, but zinc right here, anyone know it?
It's a transition.
It's 2 plus. Or sorry, 2 just plus. It's positive. So zinc plus. So zinc forms a cation, phosphorus forms a anion. And so that kind of gives you the reason why. So if you have a cation, are you gaining or losing electrons? You're gaining. And so you can kind of see what's going to happen, right? More electrons, more repulsion, which makes it larger. But for zinc, you are losing electrons. And so if you lose electrons, typically less repulsion, nuclear charge, you're going to get smaller. So that is going to give you your answer. So for this one right here, you go through the options. C is going to be your best option right here. Okay. Okay, another way you can think about this is it's asking you in the problem to compare the phosphoruses with each other and the zincs with each other, right? So that means your answer is going to result in you comparing the ion and the neutral. But a lot of the responses gives you comparing zinc and phosphorus, right? The separate one. So that's kind of clues you in that these answers are not going to be the correct answer, because here the question is asking you to compare ion and neutral, but here it's asking you to compare the two elements, which is not what the question is asking you. Because that's another way to look at it. All right, any questions on that one? So let's move on. All right, so for 15, we're still going to be looking at this chart, so just make sure you have it available. 15 says neon has a smaller atomic radius than phosphorus. So here now you're comparing neon and phosphorus. So for your answer, you're going to want to have something where you compare neon and phosphorus. Okay, let me give you guys 2 minutes to see if you guys can compare the two and get the correct answer for that. Okay. Yeah. Okay, guys, let's go over 15. So for this one, you're comparing neon and phosphorus. It says that neon is smaller than phosphorus. So if we look at the periodic table, we got neon and phosphorus. And even if you don't look at the multiple choice response, it should be pretty easy to tell neon's going to be smaller, right? What's the main reason neon's smaller?
Doesn't have electrons.
Yeah, the shells, right? Phosphorus has 3 shells. Neon has 2. Okay, and we know that another term for shells is energy levels, right? And so if you take a look at the responses, you will see A. Phosphorus has electrons in its 3rd shell, 3rd energy level, but neon does not. So that's going to be your answer. And if you look at the other responses, they kind of don't make sense. Phosphorus has more protons. If you're only looking at protons, well, then it's going to have nuclear force, so that's going to make it smaller. Neon has 2 energy levels, so 1st shell, 2nd shell. Well, technically 3, because 1s, 2s, and 2p. And then the formation of ability to form ions does not have anything to do with size. Okay? All right, easy peasy. All right, let's go to 16 now. So we're going to look at electron configuration for Zn2+. Okay, so if we take a look at Zn2+, let's look at zinc. Regular zinc's electron configuration is going to be Ar. And then it's going to be 4s2 to account for these boxes. And then it's going to be 3d10. Okay, because it's right here. All right. For Zn2+, though, how many electrons are we going to drop? 2. So the question just becomes, where do you drop it from? Do you drop them from S or D first? S. So just remember, transition metals, transition metal ions always drop from their S subshell first. And so your answer is going to be Ar and then 3d10. And I believe the answer for that was A. Okay, so just keep that in mind. Transition metal ions, they drop their 4s electrons before they drop their D subshell electrons. Alrighty. Alright, so I will give you guys your break now. And then I'll give you guys the rest of the class period to try out up to the next page, so up to 27. Again, the answer key is available for you. If you have questions, let me know so I can help you out. But I'll give you the rest of the class period. Take your break, and to prepare, in about the last 10 minutes of class, we'll take our quiz. Okay?